Today, I'm going to talk about Reynolds number, laminar, and turbulent flow. Let's take a look at the objectives of today's talk. First, I'm going to describe the laminar flow and the turbulent flow and the difference between the two and the transition flow. Secondly, I'm going to state the relationship between the parameters or the relationship used to compute the Reynolds number, how useful Reynolds number is, and where we can actually use it, limitation of Reynolds number. And I'm going to also take a look at how we can actually compute the Reynolds number for a flow in round or circular conduits. In subsequent lectures, we are going to talk about more equations, including Darcy's equation and Hayes and Williams and so on, but that's for later. So let me take a look at the flow through a faucet, and that we are pretty much familiar with that. This could be a kitchen sink, it could be really a sink in a bathroom, what have you. So as we are gradually turning this faucet on in a real slow fashion, there will be the flow of water out of the faucet in a quiet and very low velocity flow. In this case, the flow would be smooth and steady. As we are, and that flow is called laminar flow. This is a term derived from the word layer because the fluid flows in continuous layer. There will be no mixing. There will be no turbulence in this case. As we are increasing the pressure of this water, as we are turning this water more and more, we would see that now there would be the flow would be associated with some noise, and of course the flow would not be as smooth as steady that it should be. That is the turbulent flow. The flow would be more violent. And there are also transition areas between laminar flow and turbulent flow. And that is as we are gradually turning on the faucet, there will be some area in which the laminar flow started to turn into a turbulent, but it's not completely turbulent. This is more like introducing you to the concept of laminar versus turbulent flow at this stage. So that transition area, transition region of the flow is called the transition zone. Again, in that area, the laminar would change into a turbulent flow. As the name implies, turbulent flow is more violent. It's more associated with mixing of the water, and actually it was used originally for that particular purpose. It's very important in many of the equipment that we use, and in general in fluid mechanics. It's very important to discuss Reynolds number and be familiar with that number and how the calculations can be done. As we discussed previously, the work that we have looked at so far dealt with Bernoulli's equation and flow of fluids in circular conduits. We continue with that today. And of course, in that process, the diameter or inside diameter or flow diameter of the pipe plays a very important role in that process. If we look at the flow through a circular pipe in layers as such, this is one layer, this is another layer, this is another layer, and this is another layer, and so on. We can divide this into infinite number of layers, really discretizing it into these different layers and look at them differently. But if you look at it this way, you're going to have a concentric rings of fluid. We assume they're flowing in a straight, smooth path, and that is, of course, for the each layer. There will be no mixing of the fluid across the boundaries, and that is really provide us with a concept for laminar flow. Another example that is also presented in the book is if we are taking a look at an injection tube, it's dye injection tube, and we study that while it is actually streaming out of the injection tube. We can see, observe that in the laboratories that as we are increasing the pressure and the velocity of this fluid, of course, the stream would behave very differently and in a more turbulent fashion. And another example, which is another way of looking at turbulent versus laminar flow, is in looking at the picture that is shown here for an open channel flow. And in this case, one surface is exposed to an atmosphere, and the flow itself is shown here, and is going to be more in a laminar fashion. Later on, we are going to look at the open flow channels, and we will discuss how we can study this type of a flow. Originally, the application of what we discussed today was, as I mentioned, blending two or more fluids, hastening chemical reactions, and actually increasing heat transfer into or out of fluid. So for that reason, we need to study and see how the fluid would actually work. Recently, the application has also been extended to biomedical engineering and taking a look at the behavior of fluid within veins and, well, blood within veins and what have you. But those are more advanced topics that's beyond our the scope of our class here. So we're going to just stick to the introductory concept. So we try to come up with a way in which we can characterize the fluid, whether it's laminar, turbulent, or in transition. We need to have a way of describing it in engineering, a way of actually measuring it. And what would be better than having a dimensionless number? This number is called Reynolds number. Reynolds, no apostrophe S here. It's one word Reynolds and one word number, so it's Reynolds number. It actually relates the variables that are important here, being applied and they've been looked at, and these are listed here. They are the velocity of the flow. Of course, this is an average velocity of the flow, size of the flow path, fluid density, and viscosity. So Reynolds number would provide us with a dimensionless number, and that would take a look at all these important parameters and try to give us just one number, so we can say if we have a flow that's above this number, it is turbulent, and if it's below this number, it's laminar, and if it's in between, there's a transition area. So there are certain experiences, I'm sure some of you guys might have had this, including the garden hose. We try to use that garden hose. Of course, the longer the hose, there would be more pressure drop, especially if the hose is excessively long, then you would feel a pressure drop. This happens also in homes. If we have a gravity flow and the flow is in such a way that it has to go through long pipes, of course, at the end of the pipe, we're going to feel that pressure drop. This also applies to transporting liquid through pipelines. For example, transporting petroleum, the Alaska pipeline. And of course, it is such a long pipeline that in order to compensate for all that friction loss and pressure drop, we need to have these pumping stations at certain intervals to bring the pressure up again to a level in which it can flow. And again, it's going to decrease, and we need to provide along the way more pumping stations to compensate for that. One very critical example is the fire protection systems. They must be carefully designed. So, of course, if we're talking about the sprinkle systems, the pressure at each sprinkle system must be adequate to deliver the pressure that is needed to pretty much the pressure must be sufficient enough for a flow rate of water so it can cover certain areas. And that's why we have sprinkles in the sprinkle systems at so many different points. Let's take a look at the Reynolds number closer. There are four main variables that would describe the flow in a round pipe or round conduit. And these four characters they've been studied in the laboratories, and these four characters are fluid density, fluid viscosity, pipe diameter, and average velocity of flow. Mr. Osborne Reynolds was the first one, or among the first, to demonstrate that laminar or turbulent flow can be predicted by a dimensionless number. This dimensionless number is called Reynolds number. The basic definition of Reynolds number is provided here as n sub r. And as you can see, we're going to expand this equation shortly. Please note that on the numerator, this is v, and down here, this is the Greek alphabet, which I'm going to take a look at shortly. This is also the table for the Greek alphabets in case some of you guys need to have a crash course on your Greek. There are also tons of these information available out there on the other resources from the internet. So in order to reach that dimensionless number, Reynolds number, we want to make sure that the units are expressed in such a term that the end product should be a dimensionless number. Reynolds number is really the ratio of the inertial forces of an element to the viscous forces. So it's shown here, R sub E or N sub R in your textbook. It's commonly referred to as N sub R, but R sub E is also correct. Inertial forces divided by viscous forces, it's a ratio of that. And as such, it is shown as V times D times rho divided by nu, and Vd divided by this other character. It's also a Greek character in order to achieve it, but we would commonly use this type of this form of the Reynolds number. N sub R is V and D rho divided by nu, and as you can see, if you express them in the units that are appropriate, for example, velocity at meter per second, diameter in meter, density is in kilogram per cubic meter, the dynamic viscosity is also shown here. So if you can express it in these terms, you would see that all these units, they're going to drop out, they're going to cancel each other, and we would get into a dimensionless unit that we can, this is cubic meter, would be canceled with this cubic meter, kilogram by this kilogram a second, with this second, and the number would be a dimensionless number. So how can we get dimensionless numbers? That is through the process of dimensional analysis. We would take a look at the dimensions for each unit and see how we can achieve that kind of a dimensionless number. The use of dimensionless numbers in engineering are pretty popular, and we use them in different branches of engineering, including fluid mechanics. So if we have Reynolds number that are pretty high, and we are going to pretty much have, and I'm going to show it here. If we have higher Reynolds number, that means the flow is turbulent. If we have lower Reynolds number, that means the flow is laminar, and in between it's the transition zone. The limits, the upper and lower, or upper boundary and lower boundary for Reynolds number is 2000 and 4000, and this is for all practical purposes. If the Reynolds number of a flow is less than 2000, then that is a laminar flow, and if it is greater than 4000, it is the turbulent flow. And in between, we have these transition zones that we can take a look at, and we're going to solve an example problem here. And this example problem that I'm going to go over with you is actually an interesting problem. The problem is determine the range of average velocity of flow for which the flow would be in the critical region of SAE10 oil at 60 degree Fahrenheit is flowing in a 2-inch Schedule 40 steel pipe. The oil has a specific gravity of 0.89. So these information is given. We are trying to determine a range of average velocity for which it would specify the critical regions for the flow of a fluid that's given with the following information. Of course, the conduit itself is a 2-inch Schedule 40 steel pipe, and the oil has a specific gravity of 0.89. As we have already discussed, if the Reynolds number is between 2000 and 4000, that will provide us with the critical region. And so we need to express velocity in terms of Reynolds number. We set that Reynolds number then to 2000 as the lower boundary, and 4000 is upper limit, or lower limit and upper limit, and then we should be able to calculate the velocity that would be our critical region, the velocity of our critical region. So first we would use the Reynolds number and solve for velocity. Again, there are the form of Reynolds number is given here. We do some algebraic manipulation. From here we express everything in terms of velocity. Then we need to find u, d, and rho. And that's what we're going to do. D is the diameter of the pipe. It is given from the appendix in the book for a 2-inch Schedule 40 steel pipe. For the oil, we can look at the appendix and calculate this number for SAE10 oil at 60 degrees. And rho, of course, is, we already know how to calculate that, specific gravity times 1.94 slugs per cubic feet. That would be 1.73. Then we are going to put all the parameters that we already calculated. I'm going to cross those out. We're going to put those in this equation. Then V would be expressed in terms of n sub r. So velocity would be 7.05 times 10 to the minus 3 times Reynolds number. Okay. So we set the upper limit. First, we set the lower limit. So we set that into Reynolds number is 2,000. We substitute that into our previous equation, and we would calculate the V as 14.1 feet per second. Then we are going to use the upper limit, that is 4,000 in that equation, and we would calculate the velocity as 28.2 foot per second. So if the flow flows, if our fluid flows with a velocity that is shown, that is between 14.1 and 28.2 feet per second, then the flow will be in the critical region. If the velocity is less than 14.1 for practical reasons, it is going to be laminar. If it is above 28.2 feet per second, then the flow would be turbulent. That brings me to the definition and application of the Reynolds number and discussions of laminar and turbulent flow. If you have any questions, make sure to send it my way through the course website. Thank you.